This presentation is about struggling for covered message pathing on complete graphs. The definition of covered communication is to transfer message using hidden channels. Like in this example, Alice wants to transfer a message to Bob. Willie, the warden, instead of detecting the content of the message, he only wants to detect the action of transmission. There are few references for covered communication. An information theoretic approach to achieving covertness, adopted in several recent papers, relies on camouflaging messages as noise. There are also a few references for information gathering and dissemination on graphs. Here, we consider a scenario where an agent has a message that she wants to communicate to her partner who resides in a certain part of a city. Different papers use this similar model in different areas. We use the example to show our model. Alice, Bob, and Willie, they are in the same party. Alice wants to pass a note to Bob. They have some common friends in this party can help them to transfer this note. Willie, he wants to detect the action of transmission. Here we have two assumptions. For Alice and Bob, they don't know who is Willie. And for Willie, he doesn't know who is Alice, Bob, or common friend. Let's say the dissemination step. Alice can talk to any people in the party, but when she meets her friend, she can send the whole note or part of the note to the friend. And the friend can store this note. After the dissemination, the Bob can go to this party to collect this note. The Bob, he also can talk to any people in the party. And when he meets a friend who has the note, the friend can give this note to Bob. For the Willie, he also walks around in the party, but he can only detect several talks. Here we assume Willie can immediately notice the note passing when he is detecting the talk. There are two goals for Alice and Bob. For Alice, she wants to pass a note without being detected, which means the higher covertness probability. For Bob, he wants to receive this note quickly, which means the lower communication delay. First, let's talk about the method to increasing covertness probability. The first method is randomly walk. In this example, Alice will talk to any people in the party. When she meets a stranger, she will talk to the stranger without passing the note. But when she meets friends, she will pass this note to the friend. In this way, Willie cannot distinguish Alice or Bob from other people. The second method is splitting node into parts. In the example, we split the node into part 1 and part 2. Alice will pass part 1 to friend A and passes part 2 to friend B. So what is the advantage of the smaller part? First, transmitting a smaller message needs less time. Second, Alice or Bob will have a higher chance to finish transmission before Willie detects. The disadvantage is Willie will have more chances to detect. There are also some methods to reduce the communication delay. The first method is we can add more common friends in the party. In this way, the Alice will have a higher probability to meet friend. Let's see this example. For the party 1, we have a friend and a stranger. So for Alice, the probability to find a friend is 1/2. But for party 2, we have 2 friends and 1 stranger. So the probability that to find friends is 2/3. The second method is introducing redundancy into the node. In the example, the Alice can pass a node to friend A. She can also pass the same node to friend B. In this way, Bob meets either friend A or friend B is enough. Now let me introduce the communication protocol and the mobility model. Let's see this table. The Alice is the source, Bob is collector, friends are relays, and relay is the warden. First, we have a message with n bits. We can use splitting method to split this message into k chunks. Then we can use the redundancy method to encode these k chunks to get n-1 redundant chunks. Here, this graph is a complete graph with S vertices. We have R relays located uniformly on the vertices. The source and collector work randomly on the graph. Here, when the source meets the relay on the vertex, the source will pass the first chunk to the relay. It is similar as the example, the Alice will pass the part 1 of the node to friend A. The spending time is equal to 1 plus TTR. Here the TTR is the transmission time, which follows the given distribution, and the 1 is the time to discover the relay. If there is no relay on the vertex, like in the example, the Alice talks to a stranger, the source will have two models. The first, the spending time is equal to 1. There is no transmission on a non-relay node. For second, the spending time is still equal to 1 plus TTR. Here, we assume if the warden can learn the moving patterns of the source or collector, in this way, the source can hide the transmission. The source will stop after disseminate all the encoded message. For the collector, it will stop after collect K-coded message. Here is the warden model. Warden is able to monitor part of the vertices for some given time. Here we assume when the source or collector arrives at each node, the warden will monitor this node follows a uniform distribution. When the warden monitors the vertices, he can immediately detect if there is a transmission. Based on the warden model, we can get the covert probability. Here, the covert probability is defined as the probability that Alice transmits a message to Bob without being detected by Willie. To find the probability, we need to get the detection probability for each transmission first. And then we can get the covert probability in the last equation. Here, we need to emphasize that N is the number of chunks source needs to disseminate. K is the number of chunks collector needs to collect. In this figure, we show the result for the covert probability versus K for different values of N. We give the parameter values in the block. From this figure, we can have the conclusions. First, splitting method will decrease the probability. Second, redundancy will also hurt the probability. Now let's see the communication delay. The message transfer from Alice to Bob consists 3 steps. First, meeting step. The source and collector need to meet enough relays. Second, discovering step. The source and the collector need to find out if there's a relay on the same vertex. The third, transmission step. The dissemination or collection time between the source or collector and the relay. Let's see the first delay model. In this model, the source and collector only spend the discovering time, which means the constant one, on a vertex without any relay. Here we can get the expected dissemination time in this formula, and also we can get the collection time. The join time is just the sum of the dissemination time and the collection time. The figure shows the delay versus n for different values of R. Here, the R is the number of relays, n is the number of coded chunks. We have some conclusions from this figure. The first, introducing proper redundancy can significantly reduce delay. The second, increasing the number of relays can reduce the delay. In this figure, it shows the delay versus n for different values of k. Here, k is the number of message chunks. We also can have two conclusions from this figure. The first, introducing proper redundancy can significantly reduce the delay. The second, splitting message into more chunks will increase delay. For the second delay model, the source and the collector spend the same discovering time and the transmission time on each node. Here we can also get the formula of the expected dissemination time and the collection time, and then we can get the join time. In this figure, it shows the delay versus n for different values of k. Here, the conclusions are: introducing proper redundancy can significantly reduce delay. Second, splitting message into more chunks may not increase the delay much. From the simulation result of the covert probability and communication delay, it seems that splitting provides no help, but it is not true. Let's see the detection probability for each transmission. For the covert probability simulation, we know that our parameter values are w equal to 50 and m equal to 10. But here, when we have a smaller w, here w equal to 10 and m equal to 20, if we don't split the message into more than 3 parts, then the detection probability is equal to 1. And then the covert probability is equal to 0, which is very bad. The conclusions and the future works. For the conclusions, first, splitting message is not always help to increase the covert probability. Second, proper redundancy can reduce the communication delay. However, it will reduce the covert probability. Third, more relays can reduce the communication delays. For the future work, the first, we need to find more practical warden models. The second, it's better to use the regular graph